All right, y'all. So in this video, we're going to talk about chemical formulas, how we write formulas, and how we name chemical compounds. So our objectives for this unit are to be able to name ionic compounds that have either representative or transition metals, covalent compounds, acids, and bases using the IUPAC rules, which is the International Union of Pure and Applied Chemistry. We also want to be able to write the chemical formulas of ionic compounds that contain representative elements, transition metals, and common polyatomic ions, as well as covalent compounds and acids and bases. All right, so we're going to start with naming ionic compounds. So for the representative metal cations that are in groups 1, 2, and 13, these are only have one oxidation state. So we don't have to worry about their charges when we're giving their names like we do with some transition metals. So their cation name is the same as their metal name. So a charged potassium atom is just potassium, and a charged magnesium atom is just magnesium. With the anions of the representative nonmetals in groups 15 through 17, their ending, the suffix of their name changes to IDE. So you take the root of the element's name and add IDE on the end, usually at the second to the last vowel in the element's name. So fluorine becomes fluoride when it ionizes. Nitrogen becomes nitride. Sulfur becomes sulfide. Phosphorus becomes phosphide. So on and so forth. Now, with the transition metal cations and the metals that are on the right side of the periodic table, so like especially tin and lead in group 14, they have more than one oxidation state. And so their name includes a Roman numeral that shows the oxidation state or charge that they used when they bonded. So, for example, gold with a +1 charge would be written as gold with a Roman numeral 1 in parentheses to show its charge. Copper with a 2+ charge is copper with a Roman numeral 2 in parentheses to show its charge. So that is part of the ion's name. Some people think that this Roman numeral means the number of atoms of the element, but it doesn't. It's its charge. Two notable exceptions to that is that silver and zinc in the transition metals are not polyvalent. They only have one charge. So silver is always a +1 and zinc is always a +2. So we don't need Roman numerals for those elements. The polyatomic ions are, if you remember from the last unit, they are covalently bonded atoms that had to, most of the time, gain one or more electrons to fill octet. They have a given name that is on the polyatomic ion chart that is part of your reference materials. If you have two or more ions with the same nonmetal and different numbers of oxygen atoms, then there's some interesting variations to the name. So if it's two ions that have the same nonmetal and different numbers of oxygens, then the one with more oxygens has the suffix -ate, and the one with less oxygens has the suffix -ite. So for example, NO3 with a -1 charge is a nitrate ion, and NO2 with a -1 charge is a nitrite ion. If you have four polyatomic ions with the same nonmetal and different oxygens, then from the most to the least number of oxygens, the one with the most has a prefix per and the suffix -ate. So, for example, ClO4 is called perchlorate ion. The one with one less is the one with just the suffix ate. So ClO3 would be chlorate. Then one less oxygen than that would be the ite ion. So ClO2 is chlorite. And then the one with the least number of oxygens of the four has the prefix hypo and the suffix ite. So ClO, just ClO is hypochlorite ion. And you can check that by looking at your polyatomic ion chart. When we're naming ionic compounds, we're going to list the name of the cation and then the anion. So, for example, NaCl would be named sodium chloride because this is the sodium ion and this is the chloride ion. MgS would be magnesium sulfide. So again, this is magnesium ion and this is the sulfide ion. This formula would be called cesium because Cs is cesium, and SO4 is sulfate. So it would just be cesium sulfate. Ca is calcium, OH is hydroxide from the polyatomic ion chart, so this is calcium hydroxide. Sn is tin, and O is oxygen, and oxygen becomes oxide, so this is tin oxide. But since this is one of the metals that is polyvalent, I need a Roman numeral next to this one's name for its charge. To work that out, I have to remember that ionic compounds form by balancing the positive and negative charges. And oxygen's oxidation number is -2. And there's 2 of them. So -2 times 2 is -4. That means the tin, to balance that charge, has to be a +4. So this would be called tin-4 oxide. When we're writing chemical formulas for compounds, the subscripts are showing me how many atoms of the elements are present. And a good thing to note with that is that if the subscript is a 1, they are usually not written explicitly, they are implied. So for example, H2O implies that there is 1 oxygen to go with these 2 hydrogen. They did not write the subscript 1 on the water. With ionic compound formulas, the subscripts are the ratio of the cations to the anions that create a neutral formula unit. So you're trying to balance the charges out to 0. One of the easiest ways to write an ionic formula is with what we call Criss-Cross Method. So what you do is you write the metal and then the non-metal element, or if this is a polyatomic ion, you write that. You write their charges, and then you're going to crisscross. You're going to remove the positive and negative signs, and you're going to cross the numbers over to the opposite element. So using this aluminum and oxygen as an example, aluminum is a group 13 metal, so its charge is +3. Oxygen is a group 16 nonmetal, its oxidation state is -2. So when I crisscross, I get the formula Al2O3 because it would take 2 aluminum and 3 oxygen to come up with a ratio where the charges would balance out to 0. 2 times +3 is +6. 3 times -2 is -6. +6 and -6 make 0. If your oxidation number is 1, then you don't write 1 subscripts. You just write the symbol for the ion, and the 1 subscript is understood. If you have an ionic compound where both of the subscripts are divisible by the same number, so they have a common factor, you're going to factor that out. You're going to reduce the subscripts to their lowest whole number ratio. So using tin-4 oxide as the example, the tin is a +4 because this is the charge of the tin. The 4 is the charge of the tin. Oxygen, again, is a -2 oxidation state. So when I do my crisscross, I initially get SN2O4. But 2 and 4 are both factorable by 2. So if I divide both of these numbers by 2, my subscripts become a 1 and a 2. So the correct way to write the formula would be this, SnO2. If you have a polyatomic ion as either your cation or your anion, then it is treated as a whole unit. Remember that the atoms in the polyatomic ion unit are bonded together, so you never ever change the formula of the ion. You're going to crisscross the charges only. If you're going to have a subscript other than a 1 for a polyatomic ion, then you have to put the polyatomic ion in a parentheses and put its subscript on the outside of that parentheses. So for example, using ammonium sulfide, ammonium is like the one polyatomic cation that we ever see. But it's NH4 and it's a +1 ion. And then sulfide is a group 16 nonmetal, so its oxidation state is -2. When I do the crisscross, the 2 is going to go to the NH4 and the 1 is coming to the sulfur. What this means is there are 2 ammonium ions bonding with 1 sulfide ion to create that neutral formula unit. To show that, we put the NH4 in parentheses and the 2 subscript outside. And then we write the sulfur, and its 1 subscript over here is just implied. So we never ever, we would not change this 4 or any other subscript that's on a polyatomic ion. All right. With acid-base nomenclature, the majority of the acids that exist, and the ones that we're going to deal with in this class anyway, are going to be ionic compounds with hydrogen acting as the cation. There are 2 types of acids that fall in this category. The first are called binary or non-oxy acids. This is hydrogen and some non-metal anion. With their nomenclature, you're going to change the hydrogen to the prefix hydro. And then you're going to take the root of the nonmetal's name and add the suffix "ic", and then you add the word acid. So HCl would normally be hydrogen chloride, but this is a binary acid. So the name changes to hydrochloric acid. HI would be hydroiodic acid. H2S is hydrosulfuric acid, and H3P would be hydrophosphoric acid. Oxyacids are acids with hydrogen still being the cation, and you have a polyatomic anion with oxygen in it. With this, we are going to concentrate on the suffix of the polyatomic ion's name. So we don't even use the prefix hydro for them. We're just going to look at the polyatomic ion's name, and if the suffix is ATE, we change it to IC and add the word acid. If the suffix is ITE, then we change it to OUS and add the word acid. If it has a prefix like per or hypo, we leave it alone. So some examples. H2SO4. SO4 is the sulfate ion. So I'm going to change sulfate to sulfuric. So I changed the ATE to IC. Acid. So this is sulfuric acid. With HNO2, NO2 is nitrite ion. So ITE becomes OUS. So this becomes nitrous acid. With HClO4, the ClO4 is the perchlorate ion. So it becomes perchloric acid. ClO is hypochlorite ion. So this becomes hypochlorous acid. With base nomenclature, the majority of the bases that you're going to encounter are metal hydroxides. And so they are treated the same way as any other ionic compound that has a polyatomic ion. Just in this case, the polyatomic ion is always hydroxide for the anion. So you just give the metal's name and then give the name hydroxide for the polyatomic anion. So NaOH would be sodium hydroxide. MgOH2 would be magnesium hydroxide. There are some bases that are not covalent covalent compounds. Instead, we're not talking about very many of them in this class. You mostly deal with them in organic chemistry. But one to note is NH3. This is nitrogen trihydride. Its common name is ammonia. With writing formulas for acids and bases, these are still ionic compounds. You're still going to write them just like any other ionic compound. With the note that with the cation for acids is always a hydrogen ion, an H plus one. And the anion is some nonmetal or polyatomic ion. So you'd still use the Criss-Cross method to figure out their formulas. With covalent compounds, their formulas and names are different. You're going to see prefixes that tell you how many atoms of each element there are. And these are the prefixes that you need to know for the covalent nomenclature. Most of these you probably recognize out of geometry because you talk about shapes, and these have a lot of the same shapes. A couple of the notable add-ons: 1 is mono, 2 is di for this, and 4 is tetra. With covalent compounds, the elements are written in the formula and named in the order they appear from left to right and top to bottom, so from least electronegative element to most. The ending of the second element also changes to IDE, like with ionic compounds. And then you use the prefixes to tell how many atoms of each element. It is important to note that you never use mono on the first element's name. If there is only one atom of the first element, you just give its normal element name. Sometimes mono is omitted altogether, but for this, we're just going to use mono on the second element if there is one atom of the second element. So some examples: H2O, the actual chemical name of water, is dihydrogen monoxide. Di means two hydrogens. Mono means one. Oxide is oxygen. So two hydrogens, one oxygen. CO2 is carbon dioxide. So there's no mono on the carbon. All right, there's one atom of carbon, we just call it carbon. And then di is two oxygens. N2O3 would be dinitrogen trioxide. So when we're writing the covalent compound formulas, we just need to decipher the prefixes to see how many atoms of that element there are. And if the first element does not have a prefix, we assume there is only one atom of that element. So carbon tetrahydride, which is the chemical name for methane, is just CH4. There's no prefix for carbon, so we assume there's only one carbon. Tetra means four, and hydride is hydrogen when it's the second element in the formula. Silicon dioxide would be Si for silicon, and there's no prefix, so we assume there's only one silicon. Di is two for oxygen. Oxide is oxygen. So we have in this video covered how the ionic formulas are named and how they are written for the main group and transition metals, and for polyatomic ions, and for acids and bases. And we have also covered how you write the formulas and name covalent compounds using the prefixes.